Okay, so morning everyone. I'll just get my windows set up here. Okay, so I'm going to start. There's a few more people maybe to join. What I'll do is I'll give it's a very brief overview talk at the start, just to set the scene, and then I'll explain how things. It's just a not technical, so if a few people miss it, doesn't look such a big deal. This is the GPU program with OpenMP course, a very brief overview. All the material is available under standard a non-commercial share-alike license. Oh, I didn't mean to do that. These are the partners. I'll explain how this all fits together, but this is an ARCHER2 course given by EPCC, and we collaborate with a bunch of people around the ARCHER2 service. So, what is ARCHER2? ARCHER2 is the UK National Supercomputing Service. It's getting quite long in the tooth, but it's managed by UK research councils and EPSRC, but it's housed, supported, and operated by us, EPCC, and the hardware supplied by Cray as it was, but now HPE. But as part of the running that supercomputer service, we provide training as part of the computational science and engineering team, and that's one of these courses, about 60 days per year and free to all academics. I mentioned EPCC. You may know what EPCC is, but if you don't, we're the UK National Supercomputer Centre, founded, been around since 1990. The acronym comes from Edinburgh Parallel Computing Centre, but technically we're now just EPCC. We're part of the University of Edinburgh. We've been running national parallel services for over 30 years, since the very first Cray T3D in '94. There's a whole bunch of us, over 100 of us now. We do a range of academic and commercial projects. The reason I mention this is you may go away from this course and think that was all very interesting. I'd like to work with EPCC. How do I do that? Well, a lot of our staff are, in terms of technically, we're university employees, and a lot of our staff are just research associates on collaborative research grants. So we do a lot of joint research proposals getting back into European projects. So in terms of if you're thinking about wanting to work with EPCC, then and then we can just be part of a standard research grant. That's what a lot of our staff do. These are the key ARCHER2 resources. However, although we're running on this course is given as part of the ARCHER2 service, and we're running on ARCHER2, it's not about ARCHER2, it's about GPU programming, and we'll see that we're going to do it in hopefully a portable way. And so this material is there, but I don't think you'll need it for this course. Who are we? Well, this course is going to be given over a bunch of mornings, 10 to 12 over 4 or 5 days. My name is David Henty. I do a lot of training in EPCC, in particular on the MSc. My colleagues Luca, Michael, and Mark will be doing some of the other training, some of the mornings coming forward. There's a feedback form. Please fill that in. As I always say, we do take the feedback seriously. We review it at a weekly meeting, so we'll all be looked at. Good feedback is great. It makes us feel good about ourselves, and we can tell EPSRC how wonderful we are. But also critical feedback, we do take it on board. As I mentioned, I work as part of an MSc. We run an MSc in HPC and HPC in data science. We've been doing that for 25 years. You've been given access to ARCHER2 for the TA229 project accounts. There's a small amount of budget to allow you to run jobs. You can use other ARCHER2 accounts. So if you have your own ARCHER2 account, you're welcome to use that for this course. The TA229 accounts will be closed a few weeks after access ends. You'll have access for a month after the end of the course. I'm just saying this, that if you do work and programming work in that account, take copies of your work beforehand. So you'll have about a month after the course ends, and then maybe a week or so to take stuff off. However, that's your own work. Don't worry about the course materials, the slides, exercises, etc. are going to be available on the ARCHER2 website for a long time forward. So don't worry about the material. It's just if you have your own work that you've done, you want to take a copy of it. There's a code of conduct. Just generally, we expect everyone to be civil and constructive with everyone else. And so if you do have any concerns, either report it to myself or you might want to do it through there's a standard reporting form there if you have any concerns during the course. There's a timetable. We've got 5 sessions. The first 4 are more technical. This is just, I'm going to be talking about an overview today of GPU programming and GPU architectures. Then we'll get on to more details as we go on. And then we'll finish with the final half-day session practical support and consultancy. The way the course works is I'm going to give lectures here. There are a bunch of exercises, practical exercises associated. It'd be really good if you could do those. But what we're going to do is, that's why we're giving the course in short half-day sessions. The idea is in between the sessions, you go away and work on the exercises, and you can come back to us and ask us questions about them afterwards. We think that's maybe that's the way we're structuring the course. So the sessions themselves are just lectures and discussions and whatever, but we hope that in the intervening time, you'll be working on these exercises, which we'll talk about. The lecture notes, so just to show you where we are, I'll now share a different slide. Suppose it's slightly awkward, the sharing here, but let's, if I so hopefully, am I sharing the right? I'm trying to juggle too many windows as ever. Yeah, there. So you can see now, this is the ARCHER2 website. If you go to training, you'll see upcoming training. And in there, we have this course here, Message GPU Programming using OpenMP. As you see, it's happening three mornings this week. Monday, Wednesday, and Friday, I guess, and then Monday next week. And then we have the tutorial session a week on Wednesday, and all these sessions between 10 and 12. But the important point is here, I'd point you to the course materials. So the course materials here goes through, and this is just a GitHub page. But you will see that we have the exercises and the slides are all here. And so today's slides are all up here, and the exercises I'll come back to later. So I'll now go back to sharing again. So that's where all the exercise material is, and we'll come back to that again. The practical exercises, they're available on the GitHub page, but just for ease of access, they're actually available, and we'll come back to this again. They're available on ARCHER2, so you should be able to copy all so the GitHub page has the lecture slides as PDFs and all the exercise material, but just for convenience, we've stuck the exercise material on ARCHER2 as well, and you can copy that across. And I hope you enjoyed the course, but please ask questions. I said that we're recording this session, so that the presentations will be recorded and available via the website. The lecture slides are all there. You know, one of the ideas of this, you know, what the reasons we don't just give you your recording, but we have these sessions, is hopefully you can ask questions. So feel free to ask a question. I get a pop-up if you ask a question in the chat, or we can do it via video, audio if you want. Probably easiest to initially ask it via the chat. But if there are no questions, I'll just go on to the first lecture, which is basically an overview of the programming models we're going to cover. And so what I'll do is I'll maybe give a lecture for about 3/4 an hour, then I'll do a brief check to explain you how the practicals work, and we can check that people can log in and run and compile, a little break, and then come back and do the final lecture before the lunchtime break. So if I just so let's just check. You should be hopefully see. I can just. There's a bit of a delay. Okay, so what I'm going to do is going to talk about the application programming interfaces, the ways that we can program GPUs. Now, this course is going to focus very much on OpenMP, although we talk about OpenACC a bit at the end. But we are focusing, and this course, the title of this course has changed. Previously, it was called GPU Programming Using Directives, but we're focusing much more on OpenMP. So we thought that it would be better to call it GPU Programming Using OpenMP. However, I want to explain what the different programming models are for GPUs, and I think it's just useful to set the context, because it is useful to understand what methods there are for programming GPUs it helps us understand a bit how GPUs work, and it kind of motivates why we're using OpenMP. As I said during the lecture, please, if you have any questions, just ask a question in the chat. So the course is given, I said, by EPCC. HPE provide the hardware. We're part of the University of Edinburgh, and it's all funded, the ARCHER2 service, by the research councils. So the biggest issue is that when you start to want to program GPUs, you've got an application, you've heard GPUs of the future, you want to run on GPUs. There is a bewildering variety of ways of programming, APIs, application programming interfaces to program them. There's ARCHER, CUDA, HIP, OpenAC, OpenMP. There's a whole bunch of things here. Everyone says theirs is the best. So we're going to try and classify them and explain where they come from, which ones are similar, which ones are different, and really go through the pros and cons of all of them. And if you have experience with any of these, it'd be useful to get your input while I'm talking through this. So we'll try and explain the differences and similarities between these different programming models. We're going to focus on common HPC-based language. We're assuming that you're coming from a C, C++, Fortran background. I'm not going to cover Python, Julia, or machine learning framework. There are programming GPU interfaces, ways of using GPUs from Python, Julia, and obviously machine learning, but that's not what we're talking about here. We're talking about scientific and technical computational science. We're assuming your workhorse code, the parallel code that you're interested in, is written in a compiled language like C, C++, Fortran. And we'll look at the various programming styles, and we'll see there are three basic styles: directives, which is where OpenMP fits, kernels and frameworks. We'll talk about which base languages, C, C++, or Fortran. We'll talk about portability across hardware platforms, which is always very important, and particularly important at this point in time. Library support, can you call your favorite libraries, and interoperability between them, and whether they're open or proprietary, and who administers them. So just kind of setting the scene here. So there are sort of three more or less distinct programming styles for programming GPUs: kernels, directives, and portability frameworks. Now, kernels are things like, we'll talk CUDA and HIP. We run courses on this. We run a course called GPU programming using kernels. What you do is very much a bottom-up approach. You write a function, and turns out to be quite a low-level function, a function that operates on a very typically one element of your array. It's a very, very low-level thing. You write this kernel function, which contains the code to be executed on the GPU. In C, C++, and C or Fortran, it'll be a function or a subroutine. In C++, it could be a lambda. And what happens is that at runtime, that function is executed by every thread on the GPU. We'll see that GPUs have multi-threaded architectures, and they have large numbers of threads. But here, the loop over threads is implicit. So you basically define a function to be executed, and the framework will run that automatically on all the GPU threads. We'll see that the way that GPUs work is that you still have a CPU. So you have a CPU and a GPU. You run, and they're called the host and the target. But we run the program on the CPU, and the CPU passes the function or a method to the GPU. So the CPU is in control of the GPU. The CPU says, "Here's the function I want you to run it on all your threads." Now, you see we have, I've talked about having a CPU and a GPU. You're going to worry now about the data. Yes, typically the CPU and the GPU have distinct data, distinct memory spaces. And so you have to move the data as well as, you have to move the data between the two. And data movement between the host and the device is handled by library calls. And we'll see that explicitly later on. So that's the way kernels work. You write a function which typically operates on a single data item. And there is a framework for offloading that onto the GPU and running it across all the GPU threads. Directives is more of a top-down approach. It assumes you have already written some code, possibly for your CPU, so you have the code is written, and you take a block of code, typically a loop, because loops is where we have most of the parallelism in scientific and technical programming, and the directives, hints, compiler directives, to offload, to say, I want you to run this not on the CPU, but on the GPU. And so the code block will be executed on the GPU. there is some way of assigning loop iterations to GPU threads, which you may have some control over. And the number of threads can be specified in different ways. And again, there still needs to be data movement, but it's controlled by clauses on the directive. If you've done OpenMP for the CPU, you'll be familiar with this. On OpenMP for CPU program, you have the concept of shared and private data. On the GPU, extend that to having you have data which sits on the host on the CPU, or data which sits on the GPU, and you copy to and from using directives. And there may be implicit rules to do this, but the important point is kernels are very much a bottom-up approach. You start at the very finest granularity of parallelism, and then you distribute that. Directives are very much a top-down. You've written your code, and now you want to map onto the GPU. Portability frameworks are typically restricted to C++ because they typically use templates to extend C++. And basically, you have some abstract parallel execution. You basically say, I have a parallel loop. I want this to be executed in parallel. And the framework then handles how that is run. And the important point about these portability frameworks is they're portable in the sense they're designed to be portable between a CPU and a GPU. And so typically the way these work is the framework can generate code for execution on the CPU or the GPU. Now they will do that using some lower level API they may call OpenMP or CUDA, but that's hidden from you. You program at a very, very high level and say, I want to do this loop in parallel, and then the framework will be able to execute that in parallel on the CPU or in parallel on the GPU. And why they're called portability frameworks is they're designed for portability, i.e. you write the code once and it's then executed in parallel on, be it a CPU or a GPU, you don't care. When you write the code, you don't care. Now these all have their, sounds quite attractive. We'll talk about the pros and cons. So the kernel's approach, it's not so reliant on the compiler or the runtime. Your program at a very low level, you're in control of many things. You have almost complete control over what you do. So you're not reliant on the compiler or the runtime for optimization so much. And it allows for very low level tuning. We'll come back to that. So that's good. That's because it's low level. You're programming at the very lowest level. Therefore, you're not relying on other infrastructures and tools for giving you performance, and you have control over everything. That's in some senses good. However, it's less familiar to HPC programmers. It's a new programming model, so you have to learn how to program in this method. It doesn't feel like C++. It doesn't so much, or it doesn't feel like OpenMP or MPI. However, the counterpoint of being low level is that it requires more programming effort, and it's less portable. These tend to be the lower level you go, the less portable you are. So this is the classic, classic trade-off you have. Are you worried about peak performance, in which case you're prepared to learn a new programming model and do handle a lot of the issues yourself, or are you more concerned about the effort, how much time it takes, and how portable it is? So the kernel's approach, and these it fits here. This is the pros and the cons of it. The directive-based APIs, and that's what we're going to cover mostly in this course. We're going to cover OpenMP for GPUs. They require less programming effort. You've written the code and you just annotate your existing source. And they're much more familiar to HPC programmers. For example, OpenMP for GPUs is an extension of OpenMP for CPUs, which you may be familiar with. However, because they're higher level, they have fewer features. Okay, they're less. They're slight abstraction, so you won't have all the detailed control you might have for a kernel's approach. But also, they're much more reliant on compiler runtime for optimization. You annotate what you want to do. You say, this is how I want this to run on the GPU, but the actual code that runs on the GPU, you don't write. That you're reliant on the compiler or the runtime libraries doing that in an efficient way. And that can make it difficult to do low-level tuning. You may know what the GPU architecture, and we'll cover the actual GPU architectures in the next lecture. You may know what it looks like, what you want to do, but you're slightly isolated from it. It can be difficult to get the directive-based APIs to do exactly what you want. So it can make it difficult to do low-level tuning. So again, it's more portable, it's less programming effort, but then you potentially pay for slightly in terms of performance. The portability frameworks typically have their main target is, and it's there in the facility to single code base that runs efficiently on CPUs and GPUs, and that would be really nice. That is obviously something which would be good. However, they have more limited features because their target, they have a target aim of being portable, and they are very light on the compiler runtime for optimization. You really are very, very, very abstracted away from the hardware, and so it can make it difficult to do lower level tuning. And you really are, you are completely at the mercy of whoever's written the framework as to how well it runs. And they're restricted typically to C++ because they use C++ features to extend. C++ is very extensible. You extend the language in ways that make it, you have effectively a new language for programming your parallel device. But that doesn't mean they're restricted to C++. So if you have a Fortran code base or even a C code base, then you're not going to be immediately able to use these. But the base language, all the APIs we're talking about are loosely speaking sort of extensions of C, C++, or Fortran. Some of them support all three base languages. Some of them only support one, and if they support one, it's usually C++. And an important feature here is the APIs may differ in the version of the base language they support. What we mean here is if you're using the latest features in your favorite base language, then you may need, you may have to be careful to see whether you can actually port that to the GPU. Where we've seen this most commonly is in Fortran. If you're using the very latest and greatest features of object-oriented Fortran, you may not be able to offload those easily onto the GPU. The interface may say, look, we don't support these new very, very modern features of, for example, it could be C++, where I've seen it most is in Fortran. The most modern features of Fortran may not be supported for being offloaded to the GPU, so you need to be careful with that. Portability, this is important. Now, until recently, the GPU market was dominated by NVIDIA. They're the world's largest, most valuable company, trillions and trillions of dollars. However, we're now seeing competition from AMD, and a lot of the largest GPU systems in the world are actually AMD based, and Intel have tried to develop GPUs. We're not seeing them in the HPC space yet. So portability across GPU hardware has to be seriously considered. If it wasn't already, it's already been an issue, but really is important that, for example, if you're based in the UK, there is a commitment to buy the next national supercomputer to be installed in a year or two's time here at EPC here in Edinburgh. That will almost definitely be a GPU-based system, but we don't know. We don't know if it's going to be NVIDIA or AMD GPUs. So if you're developing code now, and even if you're just, even if you're only thinking about the UK, if you're going to use the national UK systems going forward, you need to have portable code which will run on more than one flavor of GPU. Now, functional portability does not necessarily imply performance portability. Okay, so just because you're able to run on two systems doesn't mean that you can. So that is important. But you need to have functional portability before you can think about performance portability. You need to, at least in principle, be able to run on both NVIDIA and AMD GPUs before you can be concerned about performance. It would also be convenient to have the same code to work on both CPUs and GPUs. But again, performance portability is an even bigger problem. They're very different architectures. And so although it is possible to write code that runs the same code that runs on a CPU and a GPU, in terms of performance, it's very hard to get performance portability. But definitely, you should not be developing code which only runs on an AMD GPU or only runs on an Intel GPU. That is not a sensible thing to do at the moment, given that we don't know what architecture. You will have access to both AMD and NVIDIA GPUs in the next 5 or so years, and you want to be able to use them both. You may very much use libraries. You may use FFT libraries or BLAS libraries, and so if you have a CPU-based code that for its performance relies on library access, you'll be interested to know, or you want to know, are they available on the GPU? Again, some APIs are better than others. Oops, apologies. Some APIs are better than others. Some APIs are interoperable with others. So for example, if you have OpenMP directives, you can call CUDA. So NVIDIA have a version of BLAS called CUDA BLAS that runs on their GPUs, and so they are interoperable. That is an important question to think about. If you're heavily reliant or you make great use of pre-existing libraries, it's important to check are they going to be available when you port your code to the GPU. So there's always a question between open versus proprietary specifications. An open specification, i.e. one maintained by some community, is much more likely to be portable across hardware platforms. I mean, in some sense, if you're a manufacturer and you're providing your own way of programming a GPU, it's in your interest to make that non-portable in some sense, because you want people to buy your flavor of GPU. It's more likely to be supported by a specification process run by a consortium of users, so there will be some procedure for some mechanism process for extending the specification. It's more likely to survive commercial implosion into vendor. There's a lot of politics going on in hardware market, and vendors and hardware and manufacturers can come and go, and also we're more likely to be concerned about backwards compatibility. However, it's much less likely to exploit vendor-specific hardware features if the next NVIDIA or AMD GPU has a particular new feature. It's going to take a while for an open specification to be able to incorporate that, whereas the vendor will clearly be able to. It'll be in the vendor's interest to make it available immediately, and also less likely to react to support new base language features. So they're slower moving but more portable. It's always the classic trade-off. So I'm going to use a particular very simple example, and we're actually going to run. I'm going to just as a mechanism for making sure that we are able to log in, compile, and run codes on ARCHER2. I will give you versions of this code in a couple of different models, but a standard low-level linear algebra operation is SAXPY, where you take, it's called SAXPY because you're doing a scalar ax plus y. It's a scalar ax plus y SAXPY. It's part of the BLAS library, and here we're assuming these are SAXPY single precision. So this is your code. You're looping over to have a very large value of n, hopefully, and for each vector element I, you're doing y is ax plus y, or in Fortran we have a very simple piece of code. What I'm going to do is to give you a flavor of how these are implemented using the various different frameworks. I'm not going to go into any detail, but I'll give you a flavor for what they look like. As I said, on this course, we're going to focus on OpenMP, but it's useful to get an understanding how other approaches work. So CUDA, which you may be aware of, is a kernel style. It's NVIDIA only. NVIDIA, said, we produce these GPUs. We'd like people to be able to program them to use them for more than just doing graphics. We'd like to be able to use them for computational science. Here's an interface called CUDA. CUDA is a kernel's interface. There's limited support in CUDA Fortran, so there isn't, but really it is very much C++. It is NVIDIA only. However, it's possible to translate HIP, which is AMD's kernels, and they're very, at least for the simpler functions, they're very, very simple. We'll see that later on. Base language is originally C. You can use C++. CUDA Fortran is a language extension, but it does require, you need compiler support. So I would say that the real strong support for CUDA is very much in C and C++. Library support is quite good, and there is somewhat interoperability with OpenMP and another directive space standard called OpenACC. Technically, the specification is proprietary to NVIDIA, but it's been around for a long time. It's a very well-established API for NVIDIA hardware, and it's very commonly used. This is how we do a SAXPY in CUDA. Now, the important point is, I'll do it kind of, what you do in these kernel-based approaches is you write a function which looks like a SAXPY. Okay, here's our SAXPY function, but there is no loop in it. So the actual SAXPY has a loop, okay? It loops over all elements I and applies this operation. In a kernel-based approach, you write a function which operates on a single value of, and there's no loop here. This says for a single value of I, y is ax plus y, but the code looks like C. So you say I have my kernel here, which has some, and you basically say y is a times x plus y. What this code up here does is it takes this kernel and it runs it across a vast number of GPU threads. It runs it across lots of threads. And so as a GPU thread, you wake up and you're given this kernel to operate. Okay, I'm going to do y is ax plus y. What value of I am I operating on? Well, there is a way, slightly bizarre way in CUDA, I think, but there's a way of saying, working out which value of I you are responsible for. So what the CUDA framework does is it distributes this kernel across lots of threads, and there is a way of working out, and there's various concepts of, this is the way of working out from my thread index which value of I am I working on. Now, we're not going to go into the detail here because we're not doing CUDA, but basically the framework distributes this kernel across lots and lots of threads, and then each thread says which value of I should I work on. But importantly, there is no loop here. What we have to do here to get this to run is that we see that we have different memory spaces in the GPU and the CPU. So I have to allocate memory on the GPU. So I have to do a CUDA malloc, which allocates, and I've got a D here which says device. So the standard nomenclature is a host, which is the CPU, and the device, which is the GPU here. So I allocate memory on the device, and I have to get the data across. There's explicit ways of copying memory from the host to the device. So this says copy the X and Y arrays from the host to the device. And then what this very, in my opinion, very bizarre syntax says is distribute this Saxby kernel here across the GPU threads. And this says to do it in blocks of 256. So basically this is saying, and we'll split this up into blocks of 256 and distribute those across all the GPU devices. But this calls this, but this is where this is the parallelism. This runs it across lots and lots of blocks, lots of threads. Now we're not going into the detail here, but that's the important model. You write a kernel function that operates on a single array element I, and this syntax here automatically executes that kernel massively in parallel across the GPU. HIP is the AMD version of CUDA. It's very similar. It's proprietary to AMD, but the API really shadows CUDA. So not all the latest CUDA features may be implemented, but there is, but it really looks very much like CUDA. HIP Fort is a way of providing a Fortran interface on the host side. You can write a Fortran code that calls HIP, but the kernels are C++ only. So it's just an interface from Fortran to the C kernels. And if you look at the HIP code, it is, in fact, it is just the CUDA code with HIP, with CUDA replaced by HIP. Okay? So, you know, this allows you to convert CUDA programs to HIP programs, to convert NVIDIA GPU programs to AMD GPU programs very easily, because there is even a script called Hipify, I think, which does this. It's exactly the same thing. You define the kernel function which runs on a single thread and operates typically on a single array element. You have to manage the memory yourself, copy to and back. You have to copy the result back here. But this strange syntax here says take this kernel and run it in parallel on the GPU across many GPU threads. So those are the two kernels approaches. Well, sorry. The final one is OpenCL. OpenCL has been around a long time. It is designed to be very portable. Okay, it's only C. There's lots of support and it's open, but it's designed to be portable across CPUs and GPUs. But the performance is kind of questionable. It's a very elegant idea, but to be honest, the performance isn't brilliant, and there's a lot of cumbersome setup code. And so I'm going to, just for fun, show you the OpenCL code here. But I'm not going to go through it because this is really just to show you there is an awful lot of setup to do. Okay, you have to, all this stuff will be done automatically for you by HIP, by CUDA. You have to do this all yourself. because it's portable, you have to do a lot of the stuff yourself, and almost a lot of stuff, and lots more stuff, even more stuff, and even more stuff. Okay, so eventually, somewhere along here, there will be a statement which actually runs the kernel. Yes, here we are. Execute the OpenCL kernel on the list. Here, this is the thing which actually says run the kernel. At the end of the day, the kernel just looks like a CUDA kernel. It is just a function that runs on a single index. But the directives are much more. There's a lot more setup to do. I thought I got a ping there. Apologies. I thought I had a question. I didn't have a question. Sorry. I got a ping. I thought there was a question. I don't think there was. So basically, it's a kernel-based approach. It aims for portability across not even just CPUs, a wide range of devices. But it's not a serious contender in the HPC space because there's just so much setup you need to do. But fundamentally, it's a framework for distributing this kernel across lots of GPU threads. SYCL is also a kernel-based framework, but it's slightly more abstracted. I believe it started off from the game space, that it was a framework for allowing you to write, to use GPUs for writing your games, but in a portable way. It's open, it's edited by the Kronos group. It is a higher level interface. So it's a kernels-based approach, but it's very heavily integrated with C++. And the kernels take the form of C++ lambdas. It's a bit more immature, and there's not many implementations, and it can generate CPU code. But it's a kernels-based approach which leverages C++ features to make it a bit more elegant. And so fundamentally, you specify a kernel y equals ax y plus y, but you have some C++ support through this SYCL interface to define your arrays, and here basically to launch this kernel in parallel. So it's a kernels-based approach, but with a potentially more elegant C++ interface than HIP and CUDA. But what we're going to do is OpenMP offloading. That's a directives approach. It's very portable across AMD, NVIDIA, and Intel. And it is possible to have CPU and GPU support in the same code base. It supports C, C++, and Fortran equally. And so if you're a Fortran programmer, then OpenMP offloading is very attractive. Library support, there's not much library support that is growing, but it is interoperable with CUDA libraries. So if you call CUDA libraries already, then you will have access to them. It's an open specification administered by the OpenMP Architecture Review Board. So OpenMP is a directive-based approach for parallel threaded programming on the CPU, which has been around for decades, and it's an obvious framework to extend for GPUs. It's now relatively mature. I mean, it's been around for a long, long time, well over a decade, but it's taken a while to reach maturity. But it is pretty mature. It's fully integrated with CPU OpenMP on the host side. In principle, it is designed for devices other than GPUs. So in principle, it's not necessarily a GPU that you're calling. There's some quirkiness in there, because currently almost everyone would use it for offloading to GPUs. However, in principle, it could be something which isn't a GPU. So again, if we're going to do an OpenMP SAXP, and you'll cover what this all means in the coming mornings, we write our code I equals 0, I less than I don't. We just write, this was the code we have written anyway, and then we say, I want to run this using OpenMP in parallel on the target. So OpenMP calls the GPU, the host, a target, which in principle could be something other than a GPU, but in practice it's going to be a GPU for us. And this code here says this is the data mapping. This says I want the Y array to be mapped to and from the GPU, because we have to, it's an input and an output, whereas the X array is only an input and that only can map to. So we'll cover all these in detail, but basically you take an existing loop which has a for statement in it, and you tell the runtime system, you tell OpenMP to distribute it. And we'll cover what these mean later on. In Fortran, it's very similar, except you have a begin and end. In C, you have the open and close braces. So this directive applies to the next code block. In Fortran, you don't have code blocks, so you have to end it. But it's very similar. And so that is the way what you do is you write standard code. This is your code, and then you offload it with these pragmas, which are formally comments here. To the language, and you offload that onto the GPU. And this will look fairly similar to you if you're an OpenMP CPU programmer, but some of this will look different. OpenACC predates OpenMP. Basically, people realized when GPUs started to become available in the HPC space, they wanted to use them, and the directives were a very good way of doing it. But it's going to take a while for OpenMP to extend its specification to include them. So OpenACC was a directives-based approach which has been around for a long time, which was there to allow you to program GPUs in a directives-based style. Now, we would probably recommend now using OpenMP, but there will be OpenACC codes out there. So it's very much, it predates OpenMP offloading, has fewer implementations because OpenMP is kind of caught up, but they're very similar. OpenACC is a little more GPU specific and was written specifically to allow you to program GPUs, but it feels like OpenMP. We would recommend now that you use OpenMP, not OpenACC, but it's been around for a long time, and you can see it looks very similar. You write your code and you annotate it, and ACC is the OpenACC. That's the directive here. That's the tag. And you have copy in, copy out, and a parallel loop directive. It's very, very similar to the Open in concept. The syntax is slightly different, but conceptually it's very similar. So those are the kernels and directives. There are portability frameworks around. Typically, as I said, they're built on C++. One is Cocos, which in principle is portable to all these AMD, NVIDIA, Intel, and CPUs. It's really come out of the US. It's administered by a consortium of mainly US labs, and it's designed to generate efficient code for CPUs and GPUs from the same source. So underneath it may call CUDA, HIP, OpenMP, C++ threads. Who knows what it does? You program at a higher level, and there's some technology underneath the hood for generating the code which actually runs on the CPU or in here on the GPU. And so, what you do is you basically have instead of doing a for, you say you have a parallel for, and basically this, you annotate your loop, and then you will be able to say, please produce code for this to run in parallel on a CPU or in parallel on a GPU. So there is some technology for doing that. So you have a new concept of a parallel for, which Cocos will then translate to, hopefully. So is there a typo? So what was the both open? I think it's okay. The Fortran. I think that's so. Is that okay? I think that's. Oh, sorry. Okay. Yes, you're right. Yes, you're absolutely right. Apologies. Yes, you're absolutely right. This is not the. You're right. Yes, exactly. Well spotted. So I just sight read that. That's good. Yes, thank you. Thanks. Yes, you're absolutely right. That's obviously been translated. Yes, you're correct. Apologies. Yeah, there is a mistake there. I'll fix that. I'll fix that later. I'll take a note to fix that. That's a very good point. Yeah, you're right. So it should be the sentinel should be ACC, like it's hash pragma ACC. There should be exclamation mark $. Thanks for pointing that out. Yeah, well done. Yeah, sorry, I just sight read that and didn't read it. So back to Cocos. Okay. That's how it looks like. Raja is another one. It's very much a lot Livermore lab. Again, the same aims as Cocos, but it does have some, has interfaces to use lower level features. It's very, very similar. it was developed by a particular lab. Again, you have a way of saying, I have a parallel loop and I want to execute this code in parallel. So just to maybe aware of these. So just as a summary, there's a wide range of programming models available for GPUs. We're going to focus on OpenMP directives. It's portable to different architectures and extends the well-established OpenMP approach for CPU multi-threading. The exercise will be done on ARCHER2 GPUs, but it really should be very. That's just because that's the machine we have, but it should be very straightforward to port, for example, to NVIDIA GPUs. There shouldn't be any problems there at all. So what I will do while I remember, thank you to Ian for pointing out that this was ACC. I guess that should just be like this. I'm not an OpenACC programmer, but I assume that's how it works. I'll check. So we're going to have just before the break. So there aren't really any particular practical exercises associated with this session, but you will start programming on Wednesday. It's important to check now that you can log in, compile, and run stuff on ARCHER2. So what I'm going to do is I'm going to go back and share a window. Go back to the GPU directives. So what would be nice, hopefully you can I just have to check. Yeah, we can see that. So there's exercises here. And the Saxby-bot PDF is just a very simple exercise to check that you can, basically it's just to make sure that you can compile and run on ARCHER2. So I will basically I'll download that just because it's easier for me to download it. So I would so if you have problems logging in, we can solve them today, but I will just show you what I hope you should do. Okay, so I will now, so those are the exercises, you should have access to them, but I will now just show you the way I think it should work. And you can try this over the break, and if you have any problems, we can sort it out maybe after 12 o'clock. I can stay online and we can sort these things out. So hopefully you should be able to see window here. Always difficult to, yeah, there we go. So I can log in. My login is TA229 hent1. You will have your own login. I'll log in, and I've already logged in today. So you would be presented with an MFA, multi-factor authentication issue there. But I just want to check that we can. You need to go to your work routine. So such as work, you need work file space TA229 /TA229 TA229 hent1. Okay, so that already exists. And then I want to do this git clone, which I just cut and paste from the PDF. If I go into the ARCHER2 GPU, that is the web page. I've already seen it has it, and there we have. Let's go into the exercises. And there they are. So the reason. Sorry. So the reason we have to get. Sorry. We need to check out a different version. Sorry, I forgot about that. We need to check out 2026-03. I haven't followed my own. Okay. Right. So now you will see that we have the slides, and sorry, I couldn't. The directory, the repository didn't look like I expected, but you have to. We're on a different branch, and then we'll see that in the slides are the things which are on the website there. But if I go to the exercises, they are. So I want to unpack the saxby.tar, and that produces a Saxby directory. And in there are simple. Now, this is just purely to make sure that you can compile and run on ARCHER2. We don't expect you to understand these codes at the moment, but there will be. You'll see on that sheet there. There's a bunch of things you have to do. So we have to do a bunch of modules, and I'll just cut and paste them in. So we have to load a bunch of modules here. Module load Rockham and a whole bunch of other magic stuff. You just have to do that. That's documented. And if we look at the code, I've given you this is exactly the code that we're going to do the hip one first, hip saxby.c. This is exactly the code which you saw in the lectures, except with a bit of this is exactly the hip offload code from the lectures again. So this is exactly the code, and I've just put in some setup. So if we do make -f makefile hip, we should be able to compile that. That will then compile. And if I sbatch hip saxby, there is a slurm file which will run that. Being a bit slow today. Okay. SQ, it's running, it's taking a while to run. It's run, and if I look at the output, you'll see that, okay, hip saxby then equals 1, 2, 3, 4, 5, 6, a million. And the checksum is correct. Okay, it does a checksum at the end to get the right answer. So let's do make -f makefile. If you look at the OpenMP, you'll see that this is just the same, except there's our code here. Start with OpenMP offload code from the lectures. I initialize it to known values so I can get the right answer. Okay, and then we should be able to make -f makefile OMP. There are some slight error messages here. It's a bit, it as a warning, but it does compile. And if I do sbatch OMP saxby.slurm, it's running. The actual code will take fraction of a second to run. The reason it takes 10 seconds is just a matter of it's completed there. And if I cat OMP saxby dash whatever, again, checksum, and it gets the correct answer. Just out of interest, the reason why I put those checksums in there is you might ask what happens. So what the sbatch does is it requests the GPU nodes on ARCHER2. It will then run these codes on the CPU, and either the hip syntax or the OpenMP directions will offload the code to run on the GPU. Here I'm logged on to a CPU front end, a login node. You might ask what happens if I run this code purely on the CPU system. Well, let's have a look. So if I run the hip code, you'll see I get the wrong answer. And that's because the hip offload must have failed. Now, there's probably an error code that comes back, but the syntax which says, please run this on the GPU using hip, okay, that syntax, which is called in the code, must have failed. And so we actually get the wrong answer, okay? So I should really, in the hip code, check there will be a return code somewhere to say that didn't work. So you can see here that code, it tried to offload to the GPU. It said there's no GPU available, so I'll do nothing. The OpenMP does a different thing. The OpenMP says there's no GPU, so I'll just run on the CPU. So it says warning, warning. So it's basically saying there is no GPU. Okay, you wanted the GFX90 GPU, there ain't one, but I'll just run the CPU. So the OpenMP has a different fallback. That's just a bit of fun, okay, to play around with. But that's why it's important to put these checksums in to check you get the right answer. So that's basically, if I stop sharing, that's basically the first lecture. What we'll do is we'll take a 15-minute break, and then I'll give the lecture on GPU. If there are any questions, please ask them, but I'll take a so you may want to have a go at logging in, activating your account, and if you have any problems, we can stay on after midday, and I'll sort them out. We can screen share and stuff. It makes things very, very easy. Okay, so this next talk covers GPU architects. It covers it at sort of two levels. One is at the conceptual level, and one is some specific examples from relatively recent architectures. Definitely the conceptual level is most important, the important thing. You know, the actual details of the architectures, AMD versus NVIDIA, and new developments will change. Concepts are really the most important one. So just to let you know that. Okay, so classic CPU programming, we have a concept that we have a processor, like you have in your laptop, and you have some memory. And you read data in and you write data out. You read in Y and X for the Saxby, and you write out Y. So that's a very simple model, and you're aware of things that actually for HPC, for scientific and technical programming, it actually tends to be this data movement, which is the limiting factor for performance. But that for performance, that's your simple model. You have a processor, whatever that is, a CPU. You have memory where you store your data, and the processor reads data from the memory, acts on it, and then writes the results out. So what affects the performance of this model? So what we're trying to do here is, I mean, you should maybe take a step back. We're trying to motivate why are we interested in GPUs for HPC programming? You know, why is everyone suddenly, or why are people in the last decade so keen on GPUs? We've had CPUs for, you know, since the 60s, 70s. What is the big deal? Well, for CPU, the number of factors affect the performance of your model. You have the clock speed, okay, the rate of issue of instructions by the processor. So your processor will issue instructions at a certain rate. For a CPU, that is in the gigahertz range, which is saying billions. It's saying that you're issuing multiple instructions every nanosecond. That's the headline figure that the manufacturers like to quote at you. The memory latency. Each time you request data from memory, it will take some time to arrive. So that's an issue that could affect your performance rate. There's the memory bandwidth. Okay. There's some overhead in requesting data. But once we're getting that data, how fast can we stream it in? How many gigabytes per second? And then the parallelism. Can I replicate the basic processing unit? Can I have more than one processor here, CPU core, or whatever, accessing the data? So clock speed, memory latency, memory bandwidth, and parallelism are the four sort of very high-level factors which affect the performance of this model. We have a processor acting on data which is stored in memory. So the important point, you may have seen this graph before, but it's definitely worth putting up, is that clock speed has plateaued since the early 2000s. So this is the clock speed of CPU frequency of this is CPUs. These are CPU frequencies for a bunch of manufacturers, although we're dominated by Intel recently. And you can see that from, like, you know, from 1970 to 2005, 30 years, the clock speed increased exponentially. Okay, so we started off with back in the 70s, clock speeds in the megahertz range, going up and up and up, and by the early 2000s, say 2005, we were in the gigahertz range, 1 or 2 or 3 gigahertz. But we can see that this is completely plateaued, and the reason is generally power limits, power and heat. Okay, you could increase the frequency of these processors, but they require too much power, too much energy and power, and they would generate too much heat. And of course, although we're using these CPUs for high performance computing, they're economical because they're manufactured for the mass market. They're manufactured for your laptop. That's why where Intel and people make their money, manufacturing CPUs for servers and laptops and such like. And clearly, a laptop is a good example. You don't want to use too much power in your CPU because then you'll run out of battery power. You don't want to generate too much heat because otherwise you won't be able to sit it on your lap. So so heat, power consumption and heat generation are clearly really important factors, and that means the clock frequencies are about a couple of gigahertz. Okay, that's fairly standard for the past, here 15, we're talking about 10, 20 years. It's very important. What about CPU memory? Well, retrieving data from RAM can take 100 or 1,000 clock cycles. It's important to realize that although the clock frequency has ramped up exponentially, the latency, the amount of time memory has lagged behind. Okay? The performance of memory has lagged, increasingly bigger gap between the rate at which you can issue instructions on the CPU side and the rate at which the RAM and the memory can deliver data. And so data from RAM can take hundreds or thousands of clock cycles to come in. Now you might say, well, doesn't that mean my CPU is spending 90% of its time idle? Well, the way we get around this in CPUs is we have caches. So data that you access regularly is stored much closer to the CPU in small caches rather than main memory, and so that latency comes down to a few clock cycles in principle. But if you do actually have to go out to main memory to retrieve data, there's a huge overhead. And once you've got there, the bandwidth is that we typically have maybe a few hundred gigabytes of memory. So the ARCHER2 nodes have 256 or 512 gigabytes of memory. But the bandwidth is a few hundred gigabytes per second, and that is often the bottleneck. Okay? You can work out that very, very rapidly that is not enough to sustain the performance, to feed the CPU with data. And so actually memory bandwidth is often the bottleneck. And so actually for HPC applications, modern processors are typically limited by memory bandwidth, latency, and bandwidth that much more than they are by clock frequency. But these are the numbers for a CPU, okay? A few hundred clock cycles, and we're getting data at a few hundred gigabytes per second. What about parallelism? Well, typically all modern processors are multi-core. My laptop maybe has 4 CPU cores. The CPUs on ARCHER2, the nodes on ARCHER2 have 128 CPU cores per node, maybe 64 per processor. However, to get that performance requires some work. Your application must be parallel, and that's why we have had since the late 80s, early 90s, these techniques for CPU parallelism, which is MPI, message passing, which is based on multiple processes, and that allows you to use very large systems, hundreds of thousands of CPU cores, or OpenMP, which allows you to do threading within a CPU core up to hundreds of threads. And so we do have parallelism in CPUs. Modern CPUs are multi-core; they have tens of CPU cores, but to use that is not automatic. You, the user, have to do some work. So why is GPU hardware different? Well, GPUs, given the name, came about for a different purpose. GPUs came about for graphics processing. So it's become very big since the 90s, and now gaming and such like, and modern audio video applications. It's very important. Graphics applications became very important, and graphics was an important enough, profitable enough field for people to build dedicated graphics processors. And graphics requires 2 things. One is it requires lots of floating point operations, lots of 3D rotations and such like. So a lot of floating point operations, which is what we want to do in HPC, but also it requires you to read and write a huge amount of memory. If you think about an HD 4K screen, there's an enormous amount of data required to generate a very high resolution image, and of course we want to refresh that image at 25, 50 frames per second. So GPUs required a lot of processing power, floating point operations, and required it to read and write a lot of memory. And so what was done is a modern CPU, and you have a physical piece of silicon. We have to use that silicon for different things. Modern CPUs have a lot of, they're very sophisticated CPUs, very, very complicated control structures. I'll talk about them. They have a number of arithmetic logic units which do add, subtract, multiply, and divide and such like. And we have lots of cache memory to ameliorate the fact that the RAM is very, very slow. GPUs are very, very simple, but we have lots of them. So they're a lot simpler, there's a lot more less control structure here and a lot less cache. We have vast numbers of arithmetic logic units, things which can do floating point operations, and also a new different kind of memory, high bandwidth memory, specialized memory, which allows the GPU to read and write data very quickly. So they're conceptually very different for built for different applications. But in my view, it's something of a happy coincidence that the capabilities that a GPU has, which is large numbers of floating point operations and very high memory bandwidth, are what we need in HPC and scientific and technical computing. And also more of a coincidence that they needed what you need for training AI models, which is what generated the huge growth in the GPU market recently. So how are they different? Well, the CPU computational cores are bigger, okay, but smaller in number. They're faster, okay, but they're much smarter. The modern CPUs are incredibly clever, and they do a lot of things which takes a lot of bookkeeping. Okay, they do out of order execution. They don't necessarily execute instructions in the order you ask them to. They work out, well, I can delay that on the fly, you know, at the nanosecond level. They're making decisions as to which instructions to execute, not necessarily in the order you supply them. Taking branch prediction, it's guessing which way that branches will go. If statements do speculative execution, it's saying, well, I'm guessing there's a 95% chance that this next F statement will go left rather than right. So I'll actually execute that code, hoping it's incredibly complicated there. But that requires a lot of infrastructure, a lot of bookkeeping to do. GPUs are really there to specialize in floating point operations, okay? Multiply, add, fuse, multiply, add, and they maybe have specialized ray tracing as well. They maybe even have tensor cores. They may even have dedicated hardware for doing small matrix operations, which is what you need for 3D rotations and such like. And so the performance of a GPU does not come from the processing capabilities of individual cores, but the massive parallelism. And so we'll see the numbers later on, but these cores are very simple, okay, and they don't operate particularly high frequencies, but we have many thousands of them. And so it's a very different approach. And they come from different target applications, but we're going to use this for doing for doing HPC calculations. So GPUs have high bandwidth, but also high latency. And so that might seem like a problem, okay? So the way that CPUs cope with latency, with high latency, is that when you read data from memory, it's stored in cache. That means if you read the same data again, it's much quicker. You have a copy locally, so you don't have to go out to RAM. So CPUs cope with the latency problem by having caches. Now we'll see that it has high latencies. How do we cope with that? Well, GPUs hide it with having multiple threads. And so what you do on a GPU is that you launch a larger number of software threads than physical cores. And so you may have thousands of physical cores. To use a GPU effectively, you need even more threads operating. You have to overload them. And that is not what you do with CPUs. On a CPU with OpenMP, if you have 64 physical CPU cores, you will run 64 CPU threads. Now, a modern CPU, modern operating systems can cope with an arbitrary number of threads, but they will be context switched in and out, okay? So it will say, oh, well, I can't run that one, I'll run that one. On a CPU, context switching is a very heavyweight operation. And it's there to say, well, I'm running David's PowerPoint, but he's not using PowerPoint now, wants to run a Firefox browser. I'll switch in and out. And if that takes a few milliseconds, then you don't really care, okay? However, the context switching to switch in and out different threads on a CPU is pretty heavyweight. And it's really quite slow. It takes a long time to switch between threads. And therefore, on a CPU model, you have the same number of, for performance in like an OpenMP application, you have the same number of software threads as you have hardware CPU cores. GPUs take a totally different approach. They say, I want you to run many, many more CPU threads than there are physical CPU cores, because whenever a thread asks for data, that's going to take a long time. I can park that thread and run another thread which has already got its data. So you hide the latency by oversubscribing, and GPUs can switch operation between different threads on about a clock cycle. So it takes, a single clock cycle, they can switch to another thread. And that's because the same reason the cores are very, very simple. They're very simple, but you can switch between them. They can switch operation to run different software, different threads very, very quickly. And so it's a very, very different approach. So the most important point to realize is that even though GPUs have a large number of physical floating point units, we have to use even more software threads than that. Tens of thousands of software threads. We oversubscribe the cores. We give them more work than they can possibly do, and that allows them to pick the thread which is active, and therefore you can hide the latency. There's a long time between requesting data and it arriving, but in that interim, you park the thread and run something else. So also, GPUs are very simple. They do single instruction multiple data. SIMD, all the GPU cores execute exactly the same operation but over different data. So when we saw that kernel, the kernel was a single thing, yi equals yi plus a times x, yi equals ax plus y. You're running the same code on lots and lots of different threads. So GPU cores run exactly the same operation but over different data. And so, rather than taking n clock steps to process n data points, you want to do the single clock step. You have n compute units. You're doing massive parallelism, and this is effective for many applications. Computer graphics, obviously, basically, computer graphics is you're doing rendering across millions and millions of pixels. Okay, so you have to apply the similar sequence of operations to a large number of pixels. That's clearly good for computer graphics. For scientific simulation, we know that many algorithms can be parallelized. We know that for many years that you can parallelize applications. And also, it's turned out recently that training AI models, input data from the same gaps can be processed. So parallelism is very prevalent in training AI models. But basically, you're using the SIMD model, the single instruction multiple data, you're operating the same operation across multiple data items. And so this is the GPU of an NVIDIA GPU. There's lots of stuff here, but what is it? Well, there is a replicated module which NVIDIA called a GPU processing cluster. And within that, they have a bunch of stuff. They have something called texture processing cluster. I presume that's for doing things like graphics, texture mapping. What we're interested in are the streaming multiprocessors. For us, an NVIDIA GPU is a large number of streaming multiprocessors. These are units which can do floating point operations. And there are lots and lots of them. You don't have to be a hardware expert to see there's loads and loads of them on here. Each streaming multiprocessor is actually divided into 4 blocks to allow for better scheduling. But the important point is you can see that the streaming multiprocessor here has 32 floating point units. And the way we think about a GPU, at least if you're coming from a CPU background, is a very large number of very wide SIMD units. So we have a SIMD unit which is 32 wide here. That's our model for a GPU. AMD is very similar. I'm not a great fan of these hardware, but there's an AMD GPU. AMD has different terminology. AMD talks about a graphics compute die, but they talk about compute engines. Okay, so a compute unit. A compute engine is replicated by a compute unit. So our basic computational unit is an SM, a streaming multiprocessor on NVIDIA, or a compute unit, a CU on an AMD GPU, and they are, if you're coming from a CPU background, very wide SIMD units. It turns out on the NVIDIA, typically it's 32 wide, and on AMD it's 64 wide. But that's how you should think of a GPU. You should think of all the threads in a streaming multiprocessor in a compute unit executing the same instruction at the same time, but on different data. So again, now the reason why I got a bit more detail about the ARCHER2, about the AMD, is that the ARCHER2 GPUs that we'll be programming are actually AMD GPUs. And so what we have is now ARCHER2, the GPUs are an add-on for experimentation. We only have four ARCHER2. We only have 4 GPU nodes, okay, very small number. They're there for development. Each has 4 GPUs, and they have 104 compute units. So if you think about it, each GPU has 104 compute units, which has 64 processors in it. So we have 6,500 compute units on each GPU, compared to with 6,420 on the CPU side. As we said, the way that GPUs work is that you have a host CPU controlling the GPU, and on the ARCHER2 they are 32 core GPUs. They're more modern than the because they're newer nodes. They're more modern than the CPUs on the main compute side of ARCHER2. But there is stuff, but they're fairly standard GPUs. So the terminology you want to talk about are threads, blocks, and warps. A thread is an item of work, i.e. a data point. So a thread is executed by a CUDA core or a stream processor at an AMD. And so this is the lowest level thing. This is the thing you program what we call the kernel. You program a single thread. A block or a work group are a collection of threads. And so we've seen that really, although you program the GPU as if it was a bunch of independent threads, they're not. In practice, they have to operate in this SIMD manner. And so blocks or work groups are assigned to these SMs or CUs. And the main thing to realize is that threads executed in SIMD fashion, and the fundamental unit on an NVIDIA GPU is called a warp. If you've ever done weaving, you have warps are the threads of, if you're making a scarf, or the warps are the threads which go long ways, and the weft, it goes left to right, where the shuttle goes through. It's a weaving analogy for threads. So there's lots, but the threads in NVIDIA GPUs execute in blocks in warps of 32 threads, or AMD there's 64, a similar number. Yeah. So you have a large number of threads, but they have to execute in these warps or wavefronts in SIMD blocks of 32 or 64. The memory hierarchy, there is some registers private to each thread, and there's also you have to be careful not to overload them. If you overload the registers, you spill out to memory, which can be very slow. But just be aware, each thread has some registers it can store temporary data in. There is cache memory. There's some shared memory which is shared between threads in the same block or work group, and there's some small amount of cache just to help some of the latency issues. But I think by far the most important. And there's also read-only memory. This is often called texture. Right? You can imagine that in a graphics context, you'll have read-only memory. You might have a texture which might be grass, and you want to apply that texture amount of terrain to make it look like you have grass over a large terrain. So because of that, GPUs have read-only memory on the GPU, and it's historically called texture memory for that texture mapping. So those are the details, but I think by far the most important, sorry, I keep saying that, and there's also L2 cache. So there are other support structures there, and they are quite complicated, but I think the main thing is to look at the comparison between the GPU and the CPU. There's also global memory, we saw. So this diagram, we have the streaming multiprocessors, which have registers, texture memory, and a small amount of cache. There is a small amount of shared cache between all the some of the SM, but out here we also have global memory, and so this is where your many gigabytes of data, where you store your main data sets. Obviously, accessing that global memory is slow, but the technique that GPU used for hiding that overhead is this very fast context switching between different threads. So this was the diagram which I really wanted to talk about. Okay, a GPU node consists of a host side. We have a traditional CPU which dispatches instructions onto the GPU, And the typical CPU has ordered tens of cores, maybe 60 or 100 cores. It has hundreds of gigabytes of memory, and the data transfer between them is hundreds of gigabytes per second. So you have tens on ARCHER2, 64, 128 CPU cores, 512 and 256 gigabytes of memory with 100 gigabytes per second, a few hundred gigabytes per second data transfer between them. The GPU, however, has a very different balance. It has thousands of cores, okay? It has fast memory, but it has less of it, so it has tens of gigabytes of memory here, but it's fast. So you have terabytes per second of data transfer between the GPU and its memory. So you can see you have orders of magnitude more GPU cores, processing cores, but you have less physical memory, but also much faster data transfer. The issue is that these are kind of bolted together, and you have to transfer data from the CPU to the GPU, and that is traditionally, until recently, been done over a PCIe interface, which has a few tens of gigabytes per second. So the big problem until recently with all GPU programming is, it's incredibly powerful GPU device, but to get data there from the CPU was over a soggy piece of string, a few tens of gigabytes per second. So data transfer between CPU and GPU was the limiting factor for a lot of programs. Now, modern advances in hardware are reducing that picture. The CPU and the GPU are becoming more integrated, and that data transfer is becoming less of an overhead, less of a bottleneck. There are a few diagrams here which are rather specific about modern hardware. So people are now moving towards having unified memory, not such a distinction between the CPU and the GPU. And so NVIDIA have unified memory in their Grace Hopper. You have separate CPU and GPU memory, but they're directly addressable. So although you have separate CPU and GPU memory, here's the CPU memory and here's the GPU memory, they can be accessed directly. So it looks like a single unified space, although actually they're physically distinct. So there are a lot of people are producing super chips which have unified memory between the GPU and the CPU. So you don't explicitly have to move data between the host and the device. However, it doesn't mean they're necessarily equal latency. So the location could still be important. So you have to be careful here. We're moving towards much more unified CPU and GPU, but you still maybe have to worry about some of the details. The Grace Hopper NVIDIA has, as you say, you have combines a Grace CPU and a Hopper GPU, and they can see each other. So you still have separate memory, CPU and GPU physical memory. This is the NVIDIA architecture, but they can be accessed directly. And there's some system level support for translating memory addresses between the CPU and the GPU. However, to get fast access, you're still going to want to have the data on the GPU. So you're still going to have GPU. You're still going to want to have GPU data on the GPU memory. This is a kind of potentially an interesting graph of the data access speeds between the CPU and the GPU memory. But I think the most important thing is really to look at the outlying point here, that basically, if you're on the CPU, if the CPU is accessing CPU memory, you have latency of about 200 nanoseconds and bandwidth of about 500 gigabytes per second. If you have the GPU accessing the GPU memory, the high bandwidth memory, the latency is by a factor of 2 more. It's 400 nanoseconds, but the bandwidth is an order of magnitude higher. It's 4 terabytes per second. So I think really there's lots of but this illustrates the big difference between the CPU and the GPU. The CPU has lots of memory, but it's accessed at here a few hundred gigabytes per second. The GPU has less memory, slightly higher latency, but can be accessed at terabytes per second, thousands of gigabytes per second, which is really quite impressive. AMD have gone a different way. They have unified memory. They don't have the distinction. They have a single piece of memory shared by the CPU and the GPU. And we don't have that on our system, but the most modern architecture. So I'm moving towards that. And so on the most recent AMD chips, we have 128 gigabytes of unified memory. The memory is in the same physical location. At the time this slide was written, it's not exactly clear what the layout was, and there'll still likely be latency and bandwidth differences, but AMD have moved towards a single piece of unified memory, 128 gigabytes of memory shared by the CPU and the GPU. That's a bit more detail than we maybe need. So basically, the summary, the key concepts are potentially have separate CPU and GPU address spaces, but very high bandwidth between the GPU and memory. And so we'll need ways of managing, saying, I want this data to be transferred from the CPU to the GPU and back again. The processing power comes from many thousands of CUDA cores or stream processors for AMD. That's the NVIDIA and AMD terminology. Each a separate thread. But the important point is that the way that you hide the latency of accessing memory is you have many more logical threads. As a programmer, you write many more software threads than physical GPU cores, and it allows the GPU to run the thread whose memory is available. If a thread requests memory, then that thread is parked until the data arrives. And this is all done at runtime, hidden from you. And the threads operate in the SIMD vector fashion, where NVIDIA call them warps, 32-thread warps, or AMD calls them wavefronts of 64 threads. But to a CPU programmer, the GPU looks like a very large number of wide SIMD units. So that's a bit of a breakneck run through. That's the end of the talk for today. Does anyone have any questions about that? So I said we will now, from next week, from Wednesday, we'll actually start doing programming to how do you access these powerful GPU processors from an application using OpenMP offload directives. But that was just kind of a brief overview of the fundamentals. Are there any questions about that?